There is a beautiful world around us which we cannot see with our naked eyes. This world contains its own oceans and valleys, cyclones and tornadoes, flowers and gardens, large animals and microorganisms, valleys and rivers, seahorses and elephants, and so many amazing mysteries. This world can be seen with the lens of mathematics only, and today we will explore a couple of wonderful facts about it. In this video, we will discuss about Mandelbrot set and its interesting properties. Let us first understand from basics that what Mandelbrot set is. Things start with a recurrence relation Zn plus 1 equals to Zn squared plus c. Here Z0 is equals to 0 and c is constant for each sequence and all the terms belongs to complex numbers. For different values of c, we obtain different sequences. Let us understand it a bit more clearly. Let us see the sequence for a specific value of c for c equals to I. Now if we want to calculate the value of z1, we put c equals to I and n equals to 0 here. In place of z0 we can put 0 and in place of c we can put I and we get z1 equals to I. Similarly, to find the value of z2 we put n equals to 1. As we have already calculated the value of z1, we can use it and we get z2 equals to minus 1 plus I. In this way, to find the value of z3, put n equals to 2 and use the value of z2. I think now we are clear with the steps to find out the further terms of the sequence. So z4, z5, z6 and so on. Now observe some sequences for different values of parameter c. For c equals to 0, we see that all the terms of sequence are obtained as 0. For c equals to 1, we see that z1 is equals to 1, z2 is equals to 2, z3 is equals to 5, z4 is equals to 26 and so on. For c equals to minus 1, z1 is equals to minus 1, z2 is equals to 0, z3 is equals to minus 1 and so on. Looking at these sequences, we can tell that for this first sequence with c equals to 0, all the terms are 0. In this second sequence with c equals to 1, the terms are increasing, and if we keep on calculating further terms of the sequence, we are moving towards infinity. And in this third sequence with c equals to minus 1, terms are oscillating between minus 1 and 0. From here we define Mandelbrot set. If the absolute value of terms is tending to infinite, then the corresponding parameter c does not belong to Mandelbrot set. In other words, Mandelbrot set is the set of all those parameters for which the sequence generated by the given recurrence relation do not diverge. Mathematically, we write it something like this. Now, if we plot all the points belonging to this set on complex plane, it does not look like a simple circle or ellipse or square. It is a complicated figure looking like a turtle, which is the first interesting thing about this set. This complex figure is emerging from a simple equation. On looking it closely, we can see that on its boundary, there is very much detailing. Here comes the second and most important interesting property of the shape. If we zoom it, we find that there are more shapes with more details. Some of these look very much similar to each other, just with some small differences. If we keep on zooming it, we keep on finding the more and more shapes and details. You can try it yourself by searching Mandelbrot iterator or generator on internet. You will find some websites or apps where you can zoom infinitely depending upon the power of device you are using. An obvious question arises here that if we do the reverse, that is, instead of zooming in, we zoom it out, will we find some points belonging to this set? Answer is no. This figure is strictly contained inside a circle of radius 2. That is why this figure has a finite area but infinite perimeter. Now, you must be thinking that either a point belongs or do not belong to this set, so there must be only two colors on the screen. But why are there multiple colors? This is because we are plotting some extra region along with Mandelbrot set. So here is how we assign colors to different points. Suppose for parameter C, whose sequence remain inside the circle of radius 2 up to 10 iterations, and then it escapes, we assign it color 1. If it remains inside the circle up to 50 iterations and then escapes, we assign it color 2. In this way, if in this way we can choose different iterations and color to be assigned. If you think there must be only two colors, actually you are correct. There should be only two colors on the screen if we plot only Mandelbrot set to be specific. That part is shown with black here. But if we assign different colors to the parameters depending upon how slow the corresponding sequence is diverging, we get to see a more beautiful mathematical world with its colorful environment. On negative real axis, if we zoom, we find teeny shapes which look very much similar to the larger part of the set. If we further zoom out, moving towards negative direction, we find more such shapes. These shapes are sometimes named as baby Mandelbrot set. Moreover, these shapes are connected with other part of the set. Actually, whole Mandelbrot set is a connected set. Depending upon the power of computer, after a specific limit of zooming, it may look like disconnected, but as you use a more powerful device which can do more iterations, you will find that Mandelbrot set is a connected set. Means if we put pen on any of its points, we can trace a path to any other point of the set without going outside the set. Now we are going to see pi hidden in the Mandelbrot set. In this set, at c equals to 1 by 4, there is a cusp. Take a point on real axis outside the set which is very close to 1 by 4. Let the point be 1 by 4 plus epsilon. Since this point is outside the Mandelbrot set, the generated sequence diverges for sure. But the closer is the point to 1 by 4, the more are the number of iterations to cross the value 2. If the number of iterations to cross 2 are n, then n times square root epsilon tends to pi as epsilon tends to 0. Let us see this numerically. Take a point 1 by 4 plus 10 raised to the power minus 6. Square root of 10 raised to the power minus 6 is 10 raised to the power minus 3. Therefore, if n is the number of iterations required to escape mod z equals 2, then n times 10 raised to the power minus 3 is 3.14, which is very near to pi. And as we decrease the value of epsilon, value of n increases and we get more accurate value of pi. This phenomenon of pi occurs at infinitely many points on the Mandelbrot set, but with certain more factors involved. To explore another property of the Mandelbrot set, we first need to understand some terms here. We know that if C belongs to M, then sequence Zn do not diverge. In this scenario, multiple cases are possible here. Case 1 is that Zn converges to a fixed value. Second case is that Zn logs itself in a cycle of 2. Means after some terms, only 2 terms are occurring alternately in the sequence. In this third case, Zn logs itself in a cycle of 3, which means after certain terms, only 3 terms are repeatedly occurring in the sequence in same order. And in this way, cycles of different integers are possible. Now, in this image of Mandelbrot set, periods of different regions are mentioned here. In this main cardioid of set, sequence are converging to fixed values. In the largest bulb attached to this main cardioid sequence of cycle with period 2, and again in the largest bulb connected to this region of period 2, there occurs a region of period 4. We can notice that if we are moving on negative real axis, we are getting regions of double period. So if we zoom and try to explore further, we will again find regions of double period like 2, 4, 16, 32 and so on up to infinity. This phenomenon is called doubling cascade. Further, if we choose a baby shape on the negative real axis, it may have period other than 2 in its primary component, but as we zoom it in negative direction, phenomenon of doubling cascade is found here also. For example, the periods 3, 6, 12, 24 and so on. We can see that on the main cardioid there are bulbs attached to it having regions of different periods. If we zoom any of this bulb and then consider the largest bulb connected to it except the parent bulb and continue in this way, here also we will find doubling cascade. Like if we consider bulb of period 3, we will find bulbs of period 6, 12, 24 and so on attached on the top of it. If we start from any other period like 5, we will find 5, 10, 20 and so on. If you find these properties interesting, then search about tripling cascade also and tell us in comments. And don't forget to like and share our video, and for more such videos, subscribe to our channel Brain Exploders. Thanks for watching.